All right. Well, good morning, and welcome back to school for summer. I'm glad you guys are here. And this is Stats 101C. Title is Statistical Models and Data Mining, or is it Intro to Statistical Models and Data Mining? I'm not 100% sure, but I'm excited to teach this class. Oh, look, this thing has popped up. I hope we're recording. Okay. Anyway, I have not finished writing the syllabus, and I'm still kind of changing things up. I've got a lot of ambition for the course. There's a lot I want to do, a lot I want to cover, but I also know we only have 6 weeks, and two classes per week. So, and the hardest thing is figuring out exactly how to do evaluation of your learning. So that's all kind of being ironed out. I know some of you are anxious to know exactly, you're trying to figure out exactly what I need to get on this grade and this and that and this and that. And I just ask that you just be patient for a few more days as I try to work everything out. My goal is always to try to be fair, to try to make your learning experience enjoyable. There's a lot I want to cover, and I've got ambition for this class. So I normally teach like computer programming courses for statistics. So I teach a lot of times the 102 series, 102A, 102B. This year they didn't give me 102C, but they gave me Stats 21, which is all about Python, and Stats 15, which is kind of like your intro Stats 10, but a lot more kind of computer heavy for data theory majors. We got a lot of students. Okay. Before I go too far, I gotta just say, there was like a glitch with the registrar's system, and it did not enforce 101A as a prerequisite for this class. You were able to enroll in this class even if you did not take Stats 101A, but that's a mistake. Okay, you absolutely do need 101A. I'm gonna assume everybody's got 101A. I'm gonna kind of assume everybody's comfortable with R and working with the tidyverse and things like that. Because there's a lot I want to do. And so if you got into this class and you haven't taken Stats 101A, I strongly urge you to drop the class and take it after you've taken 101A, because it's just not going to be fun for you, okay? You're going to feel lost, I imagine. So anyway, if that applies to you, just know that was a registrar's glitch. We told the registrar, I think, multiple times, but I don't know, the system didn't. I don't know what happened. There is some kind of disconnect, and so if you got in without taking 101A, that's the case. 102A is not like a enforced prereq. It's not a prereq in the thing, but who here has not taken Stats 102A? Okay, so a handful of you. Have you used the tidyverse at all, like ggplot? Who has never touched ggplot? Okay, so you two, I might be a little bit worried. Okay, who has never touched dplyr? Okay, so maybe a couple of you. Okay, so but from it sounds like most everyone else has at least used a little bit of dplyr, used a little bit of ggplot. Those of you who've never used ggplot, never used dplyr, I've got some resources that you're gonna have to work a little bit harder this first week to kind of get up to speed, okay? And if you're like, I don't want to do it, then this class probably isn't the right class for you. But I want to kind of just get everybody up to speed a little bit on ggplot, dplyr, the tidyverse and stuff like that. Okay, so welcome to summer session. What is this class about? It's a lot of machine learning stuff. This whole idea of statistical learning, statistical models, data mining. This is a lot about extracting information, extracting ideas from your data. We're going to be applying a lot of machine learning algorithms. There's a lot of overlap between this class and 102B. I taught Stats 102B, and there's a lot of machine learning stuff. This is going to be more focused on applications, okay? Applications of these algorithms. Whereas 102B, we really got into like, how does this algorithm work? As far as the homework problems went, I made you like code up the algorithms and things directly yourself. And in this class, we're going to try to apply them to different data sets, different things like that, okay? And again, this is summer. It's 6 weeks. It goes by fast, okay? So please don't fall behind. All right, so this is your first day. I've put up a first homework assignment. The first homework assignment should be fairly quick and easy, and the turnaround time on the homework assignments is quick. This first one, I've assigned it today. It's going to be due back on Monday. That gives you the weekend to kind of start tackling. You should start tackling it today, but it gives you the weekend to finish everything. Although this first homework assignment I think is pretty easy. It's just a lot of kind of reading and stuff, and I'll talk about like how to read. So we're going to be using a few textbooks, and this is where my ambition comes in. So a lot of other 101C courses just use this first textbook, Introduction to Statistical Learning. It's an excellent textbook, and all of these texts, basically everything you can get for free, at least an online version, electronic version. And I think a lot of you prefer electronic versions versus physical things. Certainly, like, there's something fun about holding a book in your hands, but basically, you go to this website and you can just click download right here, and it'll download the PDF, okay? And it's the full text. It's not like a junk version of the text. It's the full text. And if you want the physical version, you can go on some bookstore website and buy it, okay? Introduction to Statistical Learning. This is considered by many to be kind of the almost like one of the gold standard texts on machine learning, okay? The other text that I want to use is Tidy Modeling with R, okay? And this textbook, you actually can't buy the physical textbook yet. I think the physical textbook comes out at the end of July, but the entire text of the textbook is available to read. You got to read it in your browser, okay? So if you're on your phone, it's a little bit hard to do. I mean, you can still read it on your phone, but I would recommend using a bigger screen, and you can read the entire text in your browser. And basically, this talks about applying a lot of these modeling tools, machine learning things, in a tidy way, all right? And using tidyverse principles. I'm a big kind of fan of the tidyverse and things like that. And then there's also just the tidy models documentation, which this is an important skill, and it's not like we have a class teaching this skill, but being able to read documentation and understand documentation for programming and software is very, very important, because once you graduate and move on, you're gonna, new software is gonna be released, okay? New versions, new APIs, all of these things are gonna be released, and not everything's gonna have a course dedicated to it, but almost certainly if it's a worthwhile piece of software, it will have documentation, and you need to be able to read documentation and understand it, and that's an invaluable skill, because Stack Overflow, that's a great resource and stuff, but generally, if you can read the original documentation and understand what's going on, that's going to be important. And so I'll be referencing the tidy models documentation as well. And so the goal, my vision for the class is to work through this text, Introduction to Statistical Learning. There's a lot there. We're not going to be able to cover everything, okay? There's a lot I want to cover, but I also know the reality of our thing, of our situation, of being in the summer, only 6 weeks. And even if this were a 10-week course, I don't know if I could cover everything either, okay? But I also, in addition to covering a lot of the concepts in Introduction to Statistical Learning, I want to incorporate a lot of the practical tips of having a good workflow by using tidy models, okay? And that should, what I'm hoping is it allows you to kind of work through your data in a efficient process and things. And so we're going to be using the tidy modeling with our textbook, okay? I'm assigning homework assignments. A lot of the homework exercises are coming straight from this textbook, Introduction to Statistical Learning. And I am fully aware that because of the popularity of this textbook, a lot of people have worked through the exercises in the textbook. A lot of people have posted their answers to the exercises in the textbook. And it's tempting to search out the answers and, see how somebody did it. And again, I encourage you, don't do that, right? The purpose of the homework, the purpose of these homework exercises is so you gain that experience, okay? If you were to say train for a marathon, okay, let's say you wanted to train for a marathon and you hire someone or you team up, you join some group that says, hey, this is how we're gonna train for the marathon. Each week we're gonna run this many miles and we're gonna increase the number of the distance we run every single week. And maybe you meet up every week and they say, hey, did you do your running this week? You could lie and just say, yeah, I did the running. But if you didn't actually do it, if you don't actually do the homework, if you don't actually do the running, you're not going to be getting the proper training that you need. Yeah, question.
The homework graded on completeness or
It's going to be graded, right or wrong. There is, correctness does count. Okay, correctness does count. I don't know. I'm saying, I want you to just work through this, but I also want to make sure you take the time to get it right, okay? And yeah, so it's not just completion. I do want your responses to the homework to be correct, but yeah, I encourage you not to seek out the solutions, and I encourage you to try to work through these problems on your own. If you struggle on the homework, that's a good thing. Just like struggling at the gym, getting tired, getting exhausted, all of those things are important as far as your learning progress goes. The reason why I don't know what your true reasons are, but I imagine you want to learn something in the course and not just get the credit, right? If you just wanted to get the credit, that's something else. But I imagine you truly actually want to learn things, and so I'm working under that assumption, and I want you to put in the good faith effort. Your brain develops when it struggles through problems and things like that. That's good. Okay. During my first lecture, I like to go on big spiels about work-life balance and all of that, but again, it's summer, we're kind of in a compressed time, so I'll just have to link videos to my personal philosophies on life and homework, and some of you have already heard it multiple times because you've already taken my classes with me multiple times. So but I still feel the same way about work-life balance and just understanding that with the time we have in a day, we can't necessarily do everything we want to 100%, and some things we have to kind of cut back on, and the natural consequences of that is that you might not score 100% if you cut back on something. But let's get started. Oh, I'm still doing lecture review quizzes. If you've never taken a course with me, this is what I do instead of attendance. Okay, so I don't physically call attendance, but in my opinion, it's important that you come to lecture or at least watch the video lecture. I very much prefer you being physically present. But the way we're going to kind of enforce attendance, or at least watching of the lecture, is via the lecture view quiz. And so during the lecture, I will say, I have to switch to student view here. So in the modules for today, you would click week 1, Wednesday lecture view quiz. You would click take the quiz. And the very first answer for today is the letter A. A as an apple. A as an apple is the very first answer. And so you'll want to jot this down somewhere in your notes. And then I will give the answers to questions 2 and 3 later on in the lecture. And you will make sure you do that. The quizzes close before the next lecture, so you make sure you finish today's quiz before Friday, 9:59 a.m. and you'll get credit. Yeah, question.
Did you mention if you're going to post lectures on YouTube?
Yeah, I'm recording them and I'll post videos online. Okay, so you'll be able to follow along. Oh, I had some questions. Students asked, can this hybrid or remote or something? So it's not designed to be that way. I do record lectures, so if you don't attend lecture and you can watch, but exams are all in person, and it'll be like a group project type of thing, and so there's I'll get you the details of all of these things a little bit later, but yeah, that's what we have. Okay, so first view quiz answer today, letter A. Okay, let's we're gonna work through chapter 2 of Introduction to Statistical Learning. A lot of the stuff I'm covering comes straight from the textbook. I'm using the diagrams from the textbook, and my encouragement, or basically, this is what I want you to do. I'll cover the stuff here, and then tonight read chapter 2 in the textbook, okay? And then get started on the homework. Homework 1 starts, just covers some conceptual ideas from chapter 2 and things like that. And then I'll also introduce the Tidy Models package, and we'll kind of go through this, and I want you to also take the time to read through those texts as well. There's going to be quite a bit of reading that you'll be needing to do. Okay. So this is kind of a summarized outline of what is covered in chapter 2 of that text, Introduction to Statistical Learning. And so we're going to first just talk about what is statistical learning in the first place, and there's stuff related to that. Why do we estimate this function f and blah blah blah. And then an important part of statistical learning is how good is the model that we've created. Okay. And how do we measure that accuracy, and what are some ideas and big picture concepts regarding that. So number 1, what is statistical learning? Before we get into that, we got to talk notation, because throughout the lectures and throughout the text, you'll be seeing a lot of notation just referring to, matrices of data, vectors of data, and things like that. And I just want to kind of make sure we're all okay. So when we talk about data, we separate the predictor variables, your input variables x, from the target values y. Okay, so we're going to say our input variables are x and our target values are y. A lot of times in R, all of this comes in one data frame, right? And you have one data frame. You've got like 7 columns in your data frame. One of those is your response y, and the other 6 are your input variables. Okay, and when we talk about notation here, we're going to be separating out the input variables, those 6 columns of x, from the value that we're trying to predict, the y, the target value y. And so, so here we've got our input variables x. We've got n rows, p columns, p different variables. So each column represents an input variable, and if we're talking about a column, we're going to use bold letter, lowercase x, x1, x2, x3, etc., up to xp for the pth column, and each of those vectors x is length n if we have n observations. So if you have 100 observations, 6 input variables, you're going to have 6 of these x vectors, each of them of length 100. Okay. Each row represents an observation, and so in our case we would have 100 of these x things, and this part might be a tiny bit confusing, but the way our textbook does the notation is they just use lowercase curve italicized x. X1 consists of these 6 values for observation 1. Okay, so you've got 6 input values. They come in here, and this will be the first observation, ith observation, etc. The entire matrix X can then be described as the p columns, or it could be described as the n rows. Okay, you take each of these things and you transpose them, and that will be the input matrix X. Meanwhile, the output variable, our target values that we're trying to predict, this will be y, and we're going to assume each of these are just one value that we're trying to predict here. Okay, and this could be a numeric value. If it's a regression problem, it could be a categorical value for classification problems and things like that. Okay, so what is statistical learning? What we're saying is that in the real world, in the population, there is some relationship between some output variable y and a whole bunch of other stuff x going in. Okay, so we could say, let's predict how much someone weighs. Okay, and we could say the person's weight y is a function of, and we look at how tall this person is, and their waist size, and their gender, and et cetera, et cetera, et cetera. There's a whole bunch of variables x, and maybe some of these are important and maybe some of these are not, but there's some relationship between, I don't know what else is there, like percentage muscle mass and things like that, that relates these other variables with the output variable, how much someone weighs. Okay, or it could be what is I don't know, let's try to predict what percentage of a county voted for in the past election, what percentage of the county voted for Joe Biden. And we could say the input variables are what's the density, and what are the demographics, what percentage of the county is over age 60, and what percentage of the county is white, or what percentage of the county is this or that, and things like that. And we might have all of these things, and there might be some real relationship between x and y. Okay, now in the real world, the true thing is always offset by some error, right? There's always going to be something unexplained. You can have 2 people with the same height, same waist size, same this and that, but they might have different weights. Okay, and that's because there's just individual differences that aren't accounted for. And what we're saying is that we want to try to figure out what is the relationship between the things we can account for between x and y, and we'll just have to accept that there are things that are unaccounted for, and that's going to get wrapped up in the error term here. Okay, but we're going to assume that the mean of the error is 0. Okay, And so here is just a little diagram from our textbook. And so this is the true relationship, shows up in blue, okay? And there, the red dots that we see, these are the actual values observed. And what we see is that sometimes the red dots are above the true value, sometimes the red dots are below the true relationship, and things like that. And the idea is, can we figure out what this true relationship in blue is? Now, this blue line is generally unknown to us. We don't know the true relationship. And, we know it here because we've kind of simulated the data, okay? So we've simulated the data, so we can say this is the true relationship, and we know it. But in real life, you only see this. You only see the red dots. You can say, here we're trying to figure out, is there a relationship between someone's income and how many years of education they had? And, I don't know, 22 years of education, that's a lot, but maybe that was also me. I don't know. Right? So if you graduated high school, you have 12 years of formal education. If you get your bachelor's degree, you have 16 years of formal education. Maybe a master's degree is 18, and PhD and stuff, you end up spending a lot of time in school and, med school and things like that. So there could be some kind of relationship here between someone's income and their years of education. And again, this was simulated data, but when you're looking at data, you only get to see the actual discrete dots of points that show up. And then the thing is can we figure out what this blue line is? Can we figure out the true relationship? And we probably won't be able to figure out the true relationship in blue exactly, but maybe we can get something close to it. Okay? And so the idea of a model here is that, what are the things that factor into someone's income? And it's not just years of education. Obviously, it's also like, how long have you been working on the job? And does your boss like you? And did you get in trouble for doing something stupid, and so you didn't get promoted and things like that, right? So there's a whole bunch of things that factor into how much income you make, including like, where do you live? And so the true relationship is complicated. A model is a simplified representation. And here we're going to just say, hey, you know what? An important factor in figuring out how much someone's income is how educated they are. And I think this graph is probably overly simplified, and it just says, hey, you go to more school, you get more money, which is probably true in general, but probably not this extreme either. But certainly what you choose to study makes a big difference, right? So anyway, I'm not going to talk trash about any other major on campus, but you guys are in this. You guys are taking this class, and you're probably majoring in. I imagine the prospect of finding a good job factored into your decision for. Anyway, there's lots of good jobs for statistics and data theory majors and adjacent related things too. So, okay. So anyway, what are we doing? What's the whole point, right? And so statistical learning, is, how do we estimate that function f, the true relationship based on the data that we have? And kind of our two big motivators are, we want to use f to make predictions, right? So a lot of times this is the goal. You've got neural networks, and we just say, hey, if this data comes in, what can I print out? What can I predict? Can we, if a video stream is coming in, can we figure out like where the car should drive, right? That's like advanced stuff, and we're not going to do anything as cool as that. But that's a lot of what AI is based on, is just trying to make good predictions based on stuff coming in. And really, that's what your brain does too, right? You hear someone's talking to you, and you try to figure out what is the best response. I'm trying to predict what response I need to give to the answer, and that's kind of the question of like, can we get speech in sentient talking machines and stuff. The other part is inference. Inference, this is not as not as fancy, but the idea of inference is, hey, can we just understand a little bit of the process? Okay, can we understand some of the things that interact to understand how a system responds to different inputs and different values? Like if I tweak this thing, if I increase the heat on this part, what's going to happen to the final product, right? We want to understand that. Okay, if we're going to say we want to figure out this function f for the purposes of prediction, okay, this is kind of what it looks like, right? So we've got our inputs x and the output y. Maybe we want to figure out, predict what that is, okay? And so our notation is we've got the function that we've estimated, right? This is not the true model. This is based on past data. We might call this our training data. We say based on past data, we think this is the relationship that exists. And we call the relationship that we think exists f hat. This is our predicted model, okay, our estimate of the true function f. And we're going to say, okay, well, this is what happened in the past, and this is what I think how the system works. And therefore, when you give me this new observation, this is what I think is the output y, right? So, in the in the last election or whatever, this is what we saw happen, and this is how we think the relationship between these demographics and things work, and to find predicting what percentage voted for a certain candidate. And therefore, at the next election or whatever, assuming everything kind of still works the same, noticing that these kind of changes have happened, right? Maybe people moved away and maybe new people moved in and stuff like that. This is what we're going to kind of predict is going to happen or something. I don't know. Okay, and that represents our prediction. Okay, and in these situations, we can treat this system, this f hat, like some kind of black box. We don't actually have to understand what's happening. So things like a neural network, nobody really knows what's happening inside a neural network, okay? I mean, maybe a little bit. You've got a bunch of little like GLMs linked together and it's all intertwined and stuff, and you have 100 of these things stacked on top of each other. It's okay. We treat it as a black box and we just say, hey, data in, prediction out. Is it good? It's good, and we're happy, okay? And we don't actually care what happens inside, right? As long as it works, you're happy. It's like when you swipe your credit card, you get the product that you want. You don't actually know what is happening when it says like processing and this EMV chip and all of this verification. Like, you don't really care. Or maybe you do, but a lot is happening behind the scenes to kind of make sure this transaction is secure, so you can buy your $3.50 donut or coffee or something. Okay. Accuracy. Okay, so the accuracy of our prediction depends on two different things. Okay, and we're going to split this into reducible error and irreducible error. Okay, reducible error is the difference between the model we've created, that's f hat, and the true relationship that exists. Okay, again, the true relationship that exists is unknown to us, and we're trying to figure that out. This is the model that we predict, and we want these two things to be as close together, close as possible. We want our model to be as close to the true model as we can get. That's reducible error. Okay, the irreducible error is the residual error epsilon. Okay, so even if you knew the exact true model, there's still going to be just individual differences, right? So you can have maybe there is some true relationship between, all of these physical measurements and someone's weight, right? And you can have two people with the exact same height, two people with the exact same waist size, two people with the exact same fat index, and et cetera, all of these things, but they could end up having different weights. They might not differ drastically, but they probably won't be exactly the same either. And so that difference is irreducible. Even if you have everything exactly the same between two people with all of the same input x, their actual values y are going to be different, and that's going to be part of the irreducible error. Okay? So no matter how well we estimate the true relationship f, we can't get rid of this irreducible error, epsilon. Okay? And so if we're looking at what is the expected difference between the true value y and our predicted values y hat, okay, it's going to end up being, okay, so the true values of y are f of x plus epsilon, and the predicted values are f hat of x. And basically, the difference between this and this is the reducible error, and this part over here is going to be your irreducible error. Okay? On the other hand, if we're trying to estimate f for inference, okay, the questions that we're trying to get answers to are, which predictors are associated, which predictors are important as far as predicting the response, okay? And maybe we want to know the relationship between the response and each predictor, and is that relationship linear, or do we need to use something more complicated? And the answer is going to depend on every single situation, and maybe we want to understand, right? Okay, so let's say we have our data. This is the data that we are going to use to create a model. We call this our training data, right? So it's usually just somebody gives you data and it says, hey, fit a linear regression model or some kind of model to this. And so we're going to say we have our x and we have our y. And keep in mind, this x is not just not one value, but it's a vector associated with observation 1, and it's a vector associated with observation 2. So, x1 is going to be a vector of length p. Okay, so it's the vector of length p associated with observation I. And we're going to apply some kind of statistical learning method. Okay, and so for now, we can just pretend this is linear regression. Linear regression counts as a statistical learning method, and we'll spend kind of this, Friday's lecture will be kind of a review of linear regression, review of 101A, a lot of kind of the core concepts there, because that counts as statistical learning, okay? It counts as machine learning, and to be honest, linear regression is super powerful and can cover probably 90% of your use cases and get it to a good enough degree. And is it worth making a super complicated thing for an increase of a few points in performance? Maybe not, depends on the application. Okay, but anyway, we're going to apply some kind of learning method to the data that we have, and that's going to create an estimate of our unknown function f, right? So you get, your slope and your intercept, and your estimate of the slope and your estimate of the intercept, that counts as basically what you've estimated f to be, okay? And what we want is we want to find some kind of f hat, right? So that f hat makes a decent enough prediction of the actual values y, okay? And learning methods, we can broadly categorize them as either parametric or non-parametric. So linear regression counts as a parametric learning method. We also have non-parametric ones. So parametric methods basically say figuring out this model f, estimating it, is a matter of estimating parameters. Okay, we just have to figure out the parameters, okay? And so we have to assume there's some kind of functional form, right? So if it's linear regression, multiple linear regression, we're saying the output, your function f, is a matter of a constant, your intercept, plus some constant times variable x1, plus another constant times variable x2, plus another constant times, etc., until you get to variable xp. And it's really just a matter of figuring out how much do each of these variables factor in. Let's say you wanted to predict how much the rent of an apartment should cost, okay? And one of these things is how big is the apartment, right? Is the apartment 1,000 square feet, or is it 2,000 square feet, or is it 500 square feet? That's going to factor in, right? And how important is that, okay? And maybe something else is you have like on a scale of 0 to 10, how nice or terrible is it, right? Like if it's super clean and they have updated, like the walls are clean and the floors are nice, maybe you give it a 10, okay? And if it's like super dirty and there's bugs and, the window's broken and stuff, maybe you give it a 0 or something, right? And maybe you say, well, I'm only willing to live in a 4 or higher or something, right? I've got standards for myself, or other people might say, I'm only gonna do a 7 or higher or something, right? And then you have that. How important is that, And then maybe another factor is how far is it from the university, right? And so this one will probably have like a negative coefficient, right? If it's like if the distance from the university is very small, it'll probably cost a lot, okay? Whereas if it's like, how many minutes to campus? If it's like 30 minutes from campus, then maybe the cost will go down or something, okay? But it's still in Los Angeles, so maybe not going to go down that much. But you have each of these things, and we just need to figure out how important each of these things get factored in and stuff, right? And so it comes down to a matter of just estimating what these parameters are, okay? For every additional square foot, the cost of the apartment goes up by, $20 a month or something, and maybe not $20 a month or something, right? And then, for every kind of additional level and quality, the cost of the apartment goes up, this many dollars per month. And for every additional minute I have to commute to campus, maybe the cost goes down a little bit, okay? Or if it's on the second floor or third floor, is that a thing where like the first floor apartments cost more than the second and the third floor apartments? It should be, right? Because like nobody wants to lug their groceries up 3 floors versus, okay, anyway. You're just happy to find a place to live, I know. And so, once we figure out the model, what the form of the model should be, okay, maybe there's like a squared relationship between the distance or something, or maybe a square root relationship, I don't know, okay? Then you estimate what those parameters are, okay? And training the data, or training the model, is all about taking that training data and figuring out what is your parameter for the intercept, what's your parameter for each of these slope variables. And if we're doing least squares regression, which is a very common practice, all we do is we say, hey, let's figure out the best values that will minimize the squared error, okay? And then there's other ways that you could use for as far as estimating what these parameters should be. So, as far as parametric models though, okay, the whole problem has been reduced to estimating what those parameters are, okay? And that makes the problem a lot easier, because usually in a parametric model, you might have, say, 7 different parameters to estimate, maybe 20, okay? But basically you just have like 7, 20, some set number of things to estimate. And that's usually a simpler idea than trying to come up with something totally novel and unusual. We run into problems if this functional form that we selected, so here is a linear function, and maybe you have some other kind of form. If that functional form does not match the true relationship, then you're going to run into problems, okay? Or if you're trying to use this thing in this place where you don't have any data collected, you're extrapolating, you're also going to run into problems. And so, different ways we can deal with this issue of running into problems is we say, hey, you know what, let's make a flexible model. Let's take a model that can fit all kinds of different shapes, not just linear things, but we'll do some kind of, we'll generalize it by, applying some kind of transformation function to the variables. And if you do that, you're going to require more parameters, okay? And the other issue with running a flexible model is you run into the issue of overfitting, okay? And overfitting is the problem of basically fitting noise that exists in your data, okay? So if you gathered all of this information about apartments, okay, maybe in your data set you happen to find that apartments where the outside is painted yellow, those apartments cost less than buildings where the outside is painted white, okay? And if you factor that into your thing, you might say, okay, painted yellow, we're going to drop, $80 off the rent or something like that. And now, is that something that holds true for the general population? Probably not. But if you take your training data and you say, hey, this is the absolute thing, and let's fit the model that's going to be as flexible and include all of these things, you might end up fitting something like that, okay? And we say, well, you know what? That's actually going to reduce our predictive or performance when we generalize, okay? On the other hand, we have non-parametric models. Non-parametric models don't make any kind of assumptions about the functional form. So we don't assume linear relationships between the predicted value y and the input variables x. So we don't assume that they're linear related or some kind of functional form. We just say, hey, there's some relationship, but maybe it's just fit by some shape, okay? And non-parametric models, they can do a really good job. And we really like non-parametric models for certain applications a lot, okay? But usually it requires more data, right? So if you're going to say, if you assume something fits a straight line, what's the number of data points you need? You only need 2, right? If you're going to assume a straight line, you only need two points, and you've got an estimate of what your slope and intercept should be. It's probably not a great estimate because it's only based on 2 data points, but you've got an estimate, right? Non-parametric models, you probably need some kind of value. You need to say, hey, how much did the apartment that was 600 square feet cost? How much did the apartment that was 650 square feet cost? How much did the apartment that was 700 square feet? And you need to have a whole bunch of these data points so you can kind of get a pretty good idea of what the true relationship is. And if you have multiple apartments that were all 600 square feet and multiple apartments that were 650 square feet and something like that, you can probably get an even better estimate of what that true relationship is, okay? So non-parametric models require more data, but you won't use the wrong functional form. Okay, so here is textbook example. This blue surface, this represents the true relationship between these 3 variables. Okay, so here our response variable is a person's income, and we have the years of education and how many years they were working. Again, this is a simulated data set, so in real life it probably isn't this nice, okay? But the idea here is this blue surface represents kind of this model where we have 2 variables, okay? How many years of education and how many, right? And so the person who just started and has graduated high school, has only a few years of education and no seniority, their income is low. This would be someone over here, would be somebody who's maybe just earned their PhD, so they have many years of education, but then they just entered the workforce, so they haven't their income level isn't super high. Okay, over here would be somebody who graduated high school, so years of education is lower, but they've been working for 30 years, 25 years or something, and so they have lots of seniority. And then over here would be the people who many years of education and many years of seniority, and this is kind of the true relationship is in blue, and there's red dots. Some are above the surface and some are below the surface, and so that there's an amount of irreducible error, and it's a little bit hard to tell, but these lines going down indicate that the dot is below, and these are above. This one's above the surface and things like that. Okay, so that's the true relationship. Here is a linear model that says there's a linear relationship between years of income. There's a linear relationship between seniority and income, years of education and income. And so we're fitting basically a plane here. And, overall, we get kind of the general shape right in terms of like down here is low and up here is high, and this is somewhere in between and stuff like that. And we get this thing. But we lose a lot of kind of the nuance of this shape by fitting a simplified model, okay? So this is what we would say is not it's an inflexible model, okay? And so we miss the curvature and something like that. Here is a non-parametric model, okay? And it says, hey, we want to kind of fit just a smoothed out shape to the data points, okay? Smoothed out shape to the data points, and this is the shape that it gets. And so it's not comparing it to this. It's not exactly the same, but I would say it does a pretty good job. So this is pretty flexible. It's more flexible than this, so we have some curvature. It does a pretty good job of fitting our data. And then this one over here is another spline model, another non-parametric thing, but we said you can be as flexible as you want, okay? So over here, we gave it some, so you can imagine this as like draping some kind of sheet of material on your thing. And so this might be like taking like a thick blanket, and so you can only kind of have a certain amount of maybe, or like a thick rubber mat or something. So you get some curvature, but you can't like put in these creases, okay? And this would be like draping tissue paper over something. So you get, a bunch of dents and craters and things like that. And so if we look at this versus this, okay, this is a lot more flexible, and we've really minimized the error between the actual dots and the surface, okay? The actual dots and the surface are very small. But if we compare this to the blue model, okay, this versus this doesn't do a great job of approximating the true model in blue, okay? Whereas this one, I would say, does a better job of approximating the blue model than this one does, okay? And so when you have something that's too flexible, you end up fitting oddities in your data. So right here, here's like a little crater that appears in our surface here, and that's because this happens to be a person that has, maybe midway in their career and has a high number of years of education, but for whatever reason, their income isn't as high as we might have expected, okay? So in the true relationship, this person represents, a negative residual. Their true income is lower than what it quote should be under the true model, okay? And with a highly flexible model, it just says, oh yeah, that's a thing. If you happen to be this many years educated and this far in your career, yeah, for whatever reason, you go down. And that's not actually what's happening. This is something that's happening with this particular individual, not something that's happening in the general trend, okay? Whereas something that's a little bit more less flexible says, oh yeah, this person's lower than what we expect, okay? And it doesn't intentionally say this is a crater there, okay? And so this is a thread and a theme that you will see throughout this entire course and throughout your entire career, is there's a trade-off between how accurate we want our predictions, how interpretable we want our models. There's also going to be a trade-off between the bias and the variance and things like that, right? So over here we have a slightly more restrictive model than one that's super flexible, and this one is very restrictive. It's linear. And why do we want to do that? Okay, well, if we want to understand relationships for inference, usually restrictive models are easier to interpret, they're easier to understand, they're easier to explain. Okay, restrictive models are less prone to overfitting, and highly flexible models require lots of data for an accurate fit. Okay, on the other hand, the highly flexible models will probably give you better prediction performance. And so just kind of looking ahead to some of the methods that we'll encounter, methods that have high interpretability and less flexibility would be things like your least squares regression, also things like lasso, and when you did 101A, you did a subset selection of your variables. That it's basically linear regression, but just with even fewer variables, right? Okay. We'll look at other methods, generalized additive models, which is basically fitting splines. We'll also see the use of trees, and this gives you more flexibility at maybe a little bit of cost of interpretation. And then as you get into higher, more complicated things like neural networks and support vector machines and things like that, especially if you're going to use some kind of kernel transformation, then it becomes difficult to interpret. Okay, random forest and boosting and things like that also makes it difficult to interpret, but it might give you better predictive performance and more flexibility for your data. Overall, there's another way to talk about our statistical models, our learning methods that we'll have, is two broad categories. We have supervised learning and unsupervised learning. And so far, all of the examples that we've kind of been looking at were supervised learning, in that there are values that we want to predict. There are responses that we've observed, and we want to predict them. And we can compare, we can measure the performance of our current model by comparing what it's predicting versus the actual value. And we can say, hey, we plugged these values in and it predicted this number. It predicted 75 and the true value was 76. Hey, that's great. We plugged in the numbers and our model predicted 18 and the true model was 200. So that was not very good, okay? And we can measure that difference. That would be supervised learning. We can say, hey, good job, bad job, right? Unsupervised learning, it just says, oh, here's some stuff and there's nothing I actually want you to predict. I just want to figure out some structure in the data. And that's like a weird thing, right? But it's kind of just like, hey, can I take this data and can I create clusters or groups, right? Can we group these people together and say, hey, they're similar to each other? Okay, well, how do you measure similarity? Well, maybe we'd say, okay, we're going to put people of similar ages together. Okay, that could kind of work. That's our model for education, right? We say, oh, you're 5 years old, you all go in the same classroom. You're 8 years old, you all go in the same classroom. Okay, and then others, and that's how we cluster things, right? And then, but in college, it's no longer, age is less important. We say, hey, what classes are you interested in? And that's how we kind of cluster, right? We kind of let people self-select these kind of clusters and stuff. And depending on what you're studying, you're going to take this course or stuff like that. And so, how do we cluster? How do we create groups? That's an important question. And other things, we got dimension reduction, stuff like that. Okay. As far as supervised learning goes, where again we have some true value and some value that we're predicting. Broadly speaking, we have regression and classification methods. Okay, regression applies to when your predicted value is numeric. Classification applies when your predicted value is categorical. So examples of regression would be, let's predict the price of a house, or let's predict the cost of rent, or something like that based on different inputs. Or, can we predict how much money someone is going to spend, right? If we advertise this much, how much money are we going to get back on our campaign, right? Are we going to hit enough customers, and are they going to buy enough of our product to kind of justify this ad campaign? Okay. Classification is, what category does this belong to? Hey, does this message belong in your spam or your inbox? Okay. Does this is this person, can I lend money to this person, and are they going to pay me back? Or are they a risk and they're going to just say, hey, sorry, I borrowed your money and I can't pay you back? And then we say, oh, I'm mad at you, and we're going to tell the credit companies, but you're still out of money, right? So that could happen, right? And that's, among friends, you might have a friend in your life that still owes you $20 or something from drinks the other day or something like that, right? And basically banks do the same kind of thing, but just at a much greater scale and a much less personal experience. But they're just trying to classify people as far as, hey, can I trust this person to pay us back or not? Lots of other kind of classification problems. Okay. So for supervised learning, we want to be able to measure how good our model is. And so we want to do this. And kind of our most common measure for regression problems is mean squared error. Okay. And basically, we take the difference between the actual value and what we predicted. Right. So for observation I, for the 7th observation in the thing, the actual value is 15 and we predicted 17. Okay, it's a difference of 2 points. Okay, observation 25, the actual value is 200 and we predicted 220. Okay, it's a difference of 20 points and stuff like that. Squared error says bigger errors are a bigger problem. Okay, I'd rather have a bunch of small mistakes than have one huge mistake. Okay, so if you think about an error of 1 squared is 1, okay? And so if you have 10 mistakes of size 1, your total squared error is 1 squared times 10, a total of 10, right? Versus if you have 1 mistake of size 10, so squared error says 10 mistakes of size 1 is better than 1 mistake of size 10, right? So if you have 9 observations with 0 error, but 1 observation with 10 error, you square that 10, you get a total of 100. Okay, so your total squared error is 100 versus if you have all 10 observations have an error of 1, you square those and you get 1 squared and you get total squared error of 10. And so squared error says those bigger mistakes are a bigger problem. And so, that's why we see the phenomenon that outliers greatly affect least squares regression, right? So so when you took 101A, one of the important things they should have said is that check for outliers and check to make sure, first of all, if the outlier belongs. Maybe you should do an analysis with the outlier or without the outlier. And the reason why is because those outliers often dramatically affect the model that you end up fitting, because the squared error says these big mistakes are punished heavily, right? So that's what ends up happening. Okay, so that's something to keep in mind. And if you don't like this idea that big mistakes are punished more heavily, you can use different measures of error, right? You can just use an absolute value or something, okay? There's different problems that we run into when we use absolute values, because you can't take the derivative when you get the v with the absolute value, and derivatives get tricky and stuff like that. But there's different ways to do it. Mean squared error is it's a popular choice. Okay. we're going to talk about training data and test data. Okay, and so these are all kind of just high-level introductions to some of these concepts, and we'll get into them in shortly. But when you have data and you want to try to figure out, does my model do a good job? We don't want to just be able to predict our training data well. Okay, so our training data is the data that we have available to us. We don't want a model that just says we're able to predict every single person in this case very well. We want to say, okay, now that I've created my model, can I use it out there in the real world, and is it going to perform well, right? So we want something that performs well. It's kind of just like if you're trying to program a robot for an obstacle course. Maybe you have a training obstacle course, right? So just imagine you've got this robot that's got to like jump through hoops and jump over stuff. And one way is you can kind of like hard code the obstacles. So you can say, hey, if you start here, take 5 steps forward, then jump, and then roll over and stuff like that. And it might perform very well on this particular obstacle course. But if the competition says it's going to be on a course that you've never seen before, hard coding every single thing that says, hey, take this many steps forward and then jump and do that is not going to work well, because it's going to probably have a different layout, right? And so you need to kind of create a design that says, okay, first look to see if it's got this, and then you've got to kind of program it accordingly. And similarly, if you have your training data and you say, I want to make perfect predictions for my training data, you can get a good model that works really well for the training set, but then when you try to take it out into the real world, it's going to do poorly. Now, testing how it works in the real world requires you to gather new data. And so a lot of times, what we want to do is we'll take the data that we have and we're going to intentionally split it into a training set and a test set. We'll talk about all of that. But a lot of times is we're going to measure our performance on the training data, and then we measure our performance on new data that it hasn't seen, and that's called our test data. And we want to measure kind of the mean squared error, or the amount of error that we have there. And so we have some ideas here. Okay, in general, if your model is super flexible, you're going to have lower training mean squared error. Okay. So, super flexible models like, splines can fit, a wider range of possible shapes. Okay. Less flexible methods, generally easier to interpret. Okay. But when you take your model and you put it onto the test set, the very flexible model can end up having a much higher mean squared error than something like a simple model. Okay, so I'm going to show you a bunch of graphs. These are straight from a textbook. And what you're going to see is on the left, there's the true relationship that's going to show up in black. And we're going to fit 3 different models: orange, blue, and green. Orange is going to fit a straight line. Blue is going to fit a smoothing spline, and green is also going to fit a smoothing spline. But when you fit smoothing splines, there's different options. And one is you can say, I want it to be less flexible, and one is I want it to be like super flexible. Okay, and it's kind of the idea between, you can think of fitting a smoothing spline as like bending a cable, right? And so you have the data and you say, okay, I want to kind of fit this thing. And so a less flexible thing is like taking this thick cable and you're trying to make a curve with this thick cable. And there's only it's really hard to get like really tight turns when you have such a thick cable. Okay. The other, you can also have a smoothing spline where it's like almost like thread, and you can have like really tight turns in it and stuff like that because it's more flexible. And so that's kind of what we'll see. So the blue line is going to be like a less flexible, medium flexibility smoothing spline, and green is going to be very high flexibility. Okay, and then on the right hand side, you will see two lines, okay? A gray line and a red line, okay? And on the gray line, you will see an orange square, a blue square, and a green square. And on the red line, you'll also see an orange square, a blue square, and a green square. And those represent how much error there is in the training data for the linear blue smoothing and the two smoothing splines versus how much error there is in the test data for the different models. Okay, so let's start off with this. The true relationship is in black. Okay, and then here the circles represent random data generated around the true relationship in black. And we have the three different models. Yellow is the straight line. Blue approximates the true relationship pretty well. Doesn't quite get this little twist here, but it does a pretty good job. Okay, and then green says it's super flexible and it's trying to fit the training data. And so it says I'm trying to minimize like the distance between any of the points, and so it's quite wiggly. Okay, over here in the gray is the training data. How much error is there between the yellow line and the actual the data in our training set? And there's a lot. Okay, like 1.7. Okay, what about for the blue line? The blue line reduces the amount of training data quite a bit. And then for the green line, the amount of error in the training data is very low. Okay, because it's very small distances between the green line and any of these data points. Okay, so it has very low training data error. Okay, the red line is though for the test data. The test data is like a new data set that was generated around the black line. And so when we generate the test data around the black line and we try fitting it to the yellow straight line, we get a lot of error. It says it doesn't do a very good job. Okay, when we compare it to the blue line, it drops down and we say, okay, we got quite a bit of less error. But then when we compare it to the green line, okay, this green line overfit this data. And so it says, hey, you know what? When you get an observation with x equal to 60, we're going to predict, I don't know, 10 point something. We're going to predict up here. And in reality, it should be closer to, say, 8 or 9 or something like that, okay? And so it actually ends up having a higher amount of mean squared error on the test data. So you end up seeing, for the test data, you end up seeing this U shape, saying that as the models become more flexible, the error starts to go back up in the test data, okay? As the models get more flexible, the training data goes down. We're able to fit all of the nooks and crannies in our training data, so this goes down. But for the test data, this actually goes up. And what we see is that kind of the model with medium flexibility has the best performance, okay? And that's what this whole slide kind of talks about here. Something similar over here, the true relationship is in black. And if you look at it, there's a little bit of curvature. It's not a perfect straight line, but a little bit of curvature, okay? And so the orange line, which fits a straight line, has very little error, okay? The blue line, which has just a tiny bit of curvature, has even less error, okay? And then the green line, for the training data, it says, let's minimize all the error. Let's try to fit every single little nook and cranny here. And it says, hey, you know what? I don't like this outlier, so let's make sure our model goes up there. This one's down here. Let's try to get down there and stuff like that. And so it has even less error on the training data, okay? But then when we take test data, which we don't see here, okay, but we generate new test data around the true relationship, what we see is that, the orange and the blue line have practically the same amount, okay? Well, because if you look at it, the orange and the blue line look almost exactly the same on this thing, okay? Orange is straight, blue has a little bit of curvature, but they look pretty much the same on this graph. And so the amount of error here, both of them very small. And what we see is that the green line, although it has the best performance on the training data, has the worst performance on the test data. So as we increase the more flexible. And so at this point, what model should you use? Should you use the blue model? The blue model technically has the least amount of error in the test data set, but is it the best? Is it the best? If your sole measure is test data error, then yes, blue model is the best. But if somebody said, hey, I want you to explain the relationship between X and Y, it's a lot easier to explain just a linear thing. You can just say, as X goes up 20 points, we expect Y to go up 2 points, right? So every point X goes up, Y goes up by 1/10 of a point. That's a linear relationship. That's a lot easier to explain. It's a lot easier to explain a linear relationship. And is the performance as good? It's technically a tiny bit worse. Does it really matter? Probably not. Okay, the true relationship isn't a linear thing. There's just a tiny bit of curvature. But are we really going to get upset about this? And there's just kind of it's easier to explain. Yeah.
How do you calculate the flexibility?
Yeah, so this is, that's not explained as far as these graphs go. This, I think what they did was they fit a smoothing spline for basically everything here. And yeah, I guess we'll get to it on smoothing splines, but there's a parameter, like a lambda or gamma parameter for the smoothing spline that says, how much do we punish the second derivative, the curvature, and you can set that anywhere from, a high amount to a low amount. And if you set it to a low amount, you have more flexibility. If you say, I'm going to punish this the curvature a high amount, you have less flexibility. And if you punish it a certain amount, basically your flexibility, it becomes a linear model. So anyway, all to say is that you can adjust a parameter to get different measures of flexibility. I don't know exactly what was used to get these particular values, and you can see it's not quite it's not a linear scale, right? It goes 2 to 5 to 10 to 20, and the distance between 5 and 10 is the same distance as 10 to 20. So it's it's like on some kind of logarithmic scale, kind of. No, it's definitely a log scale, right? This is times 2 is the same distance. So I'm not 100% sure how they calculated this measure of flexibility, but it is something you can kind of play around with. And so, we haven't gotten into fitting these models yet. This is just kind of a higher level conceptual idea. But yeah, we'll talk about fitting like a low S curve, and there's a parameter like the bandwidth, or you can fit a smoothing spline, and there's parameters there for how flexible you want the model. Okay, but this is the idea here. A linear line, probably easiest to explain, and so you get the benefit of easy explanation. And at what cost does it come at? It's a very low cost. You get a tiny bit more test MSE, and I would say it's probably worth it. Probably worth it for that ease of explanation and ease of understanding. Because if you're trying to explain, okay, well, what's the blue line saying? Well, it says it's kind of linear, but what we got to do is we got to adjust this a little bit. That's what we have. Okay, here's another example. The key here is the linear line does a really, really bad job. Okay, so depending on the situation, this is what we have. And kind of the theme that we've seen is that something in the middle, in terms of the amount of flexibility, is probably your best. You don't want something super inflexible. You don't want something super flexible. In terms of test MSE, something in the middle performs the best, whereas linear relationships are great when linear relationships work, but if not, linear relationships do bad. Okay, and so this illustrates what we call the bias-variance trade-off. Okay, and that we always kind of have these two kind of competing forces. Do we want to shrink the bias? Do we want to shrink the variance? And they're kind of these forces at play. Okay, bias is the difference that arises from using a model, a simplified version, to approximate or to describe usually a complicated process, right? So the data that's generated in the real world, follows some kind of complicated process, and we're trying to simplify that using a model. Okay? And so, linear regression assumes the relationships between your x variables and y are linear. Okay? And if the true relationship is not linear, then you have bias. Okay? So the variance, on the other hand, is how much does your estimated model, how much does it change or depending on the training data that you have? Okay? So if I gave you the homework assignment, I say fit linear data or linear model to a certain set of data. And some of you I give one random set of data, some of you I give another random set of data, and others of you I give a different random set of data. They're all of these random data are generated from the same true model. Okay? Your linear models are going to be different, right? But will your linear model be drastically different from someone else's? Probably not, okay? Because as far as linear models go, you just have a few slope parameters to estimate and intercept parameter to estimate. They might differ by a little bit, but how much do your linear models differ from someone else's? Probably not very much, even though you have different training data sets, okay? On the other hand, if you have a very flexible model, like this green spline model that gets very wiggly, okay? How your model looks is probably going to differ quite a bit from someone else's if they have a different training set, okay? And that's the idea of variance. How much do the models vary from one training set to another, okay? And so if we talk about the expected test MSE, this is for some test data point y0, we want to compare that versus the predicted value, okay? And we see what's the expected difference squared here. That's going to be the variance of our predictions for x0 plus the bias of our predictions squared and some amount of irreducible error that we just can't get rid of, right? Because the actual values also have some amount there, okay? And so these things add up, and if you want to decrease the variance, you're probably going to increase the bias. If you want to decrease the bias, you might end up increasing the variance, okay? So as the bias decreases, the variance increases, and that's just kind of this bullet points didn't work out, but basically here's just a few examples. The true model is going to be shown in black. I'm going to fit a highly flexible model in green, less flexible model in blue. And so the true relationships in black, we have this less flexible model in blue, which ends up fitting here. So down here it's below the true relationship, and in green we get this very flexible model, okay? This is random data, okay? I'm going to fit using the same true relationship. So you'll see the black line remains the same in all three of these graphs, okay? The black line remains the same, and the random data, which is our training data, varies from one graph to the next, right? So the training data that appears changes, okay? And you can see the green line, which is very flexible, changes quite a bit from plot to plot, okay? The black line is exactly the same. That's the true relationship. That doesn't change. How much does the blue line change? Going from plot to plot, it changes a little bit, okay? But not very much. Changes a little bit, but not very much. Whereas the green lines change quite a bit from plot to plot, okay? And so this illustrates that there's less variance in the blue line. Going from one random data set to another random data set, the blue line doesn't change very much, okay? The green line has a lot of variance. It changes a lot from one random data set to another, okay? However, if you look at the blue line, it is consistently lower than the black line here, okay? there's bias, okay? So even if I did 1,000 of these things, probably every single blue line is going to consistently underestimate what the true value is right here, okay? It's consistently below here. That's the bias, okay? If we average all the blue lines together, it will consistently be below the true line. So that's the bias, the difference between the kind of the fitted value, the average of the fitted values from the true thing, okay? If you look at the green line, though, it's consistently around the black line. So if we averaged all of the green lines together, we're probably going to get something close to the true relationship. But so we're going to have less bias there. But again, high variance because the green line changes drastically from one random data set to another. Does that kind of make sense there? All right, so that's kind of this idea of the bias variance trade-off. And that's going to just be kind of something that we see consistently and throughout the course, okay? Classification problems, how do we measure the error? One is just to measure the classification error rate. So if we predict this is going to be category blue and the true value is category red, that's an error, okay? If we predict category blue and the true value is category blue, then that's not an error, that's correct, okay? And so the error rate is just how many mistakes did you make versus how divided by how many observations total do you have, right? So it's just like a score on an exam, right? How many did you get right is basically, or how many did you get wrong is the error rate there, okay? And that's how we measure accuracy. And so, again, this is just a high-level introduction to some of these concepts that we're going to be revisiting, during our remaining time. So we have the k-nearest classifiers. K-nearest neighbors classifier just says, hey, look, let's take a test point. Let's look at other observations in our training data, and let's pick the nearest neighbors. Nearest neighbors being measured by Euclidean distance, and we look at the classifications of our neighbors, and we say, okay, well, my nearest neighbors are red, or my nearest neighbors are blue, and therefore this test case is going to get classified as red or blue. Okay, so the training data are these circles in orange and blue. And so here, this green dot here that I've drawn, this represents a test case, okay? So for this test case, we say, what are my 3 nearest neighbors? This is going to be k equals 3. My 3 nearest neighbors are this point, and this point. These are my 3 nearest neighbors. And if I look at these 3 points here, 2 of them are orange and 1 is blue. And therefore, the 3 nearest neighbors, out of the 3, 2 of them are orange, so this test case is going to get classified as orange. Okay. Over here, we can ask, here's a test case. We say, what are my 3 nearest neighbors? And the 3 nearest neighbors are this point, and this point. And out of these 3 neighbors, 2 of them are blue and 1 is orange, and so this is going to get classified as blue. Whereas if I move just a little bit over here, okay, if I move down to here, say this point right here, this thing is blocking me. But now my 3 nearest neighbors are these 2 orange points in blue, okay? We're now a little bit further away from here. So this point, the 3 nearest neighbors are orange, orange, blue, and therefore this one's going to get classified as orange, okay? So basically you just say, at a certain location, what are the nearest neighbors, the 3 nearest neighbors? And so for this point, the 3 nearest neighbors are probably this, this, and this, these 3 points. 2 are orange and 1 is blue, and therefore it's going to get classified as orange. Whereas if I go, say over here, what are the 3 nearest neighbors to this point? Probably this, this, and this, these 3 points. And so with these 3 points, we have blue, blue, orange, and we're going to get blue. Over here, what are the 3 nearest neighbors? You get 3 blue, and so this is all blue and stuff like that. Okay, and that's basically how this map is drawn. Okay. you can change however many k you want. So here we've been looking at like the 3 nearest neighbors. We could say, what if I wanted to look at the 1 nearest neighbor or the 5 nearest neighbors or something like that? Well, you get different kind of things here. So this is just a diagram that kind of showing the same ideas of bias and variance. The dotted purple line is the true boundary, okay? The dotted purple line is the true boundary between the blue zone and the orange zone. That's the dotted purple line. And we generated some data, okay, with some noise. And so, we have blue points generated over here, but because of random noise, sometimes we get orange points generated on the wrong side of the boundary, okay? So with k equal to 1, and sometimes we get some blue points generated on the wrong side of the boundary as well. And so with k equal to 1, it tries to say, hey, what's the nearest neighbor? And we get, these little exclaves and enclaves of where orange and blue exist. And this ends up being the thing. And so we have high variance. So if we generated another random data set, what gets shaded orange and blue will probably look quite a bit different because of random noise. We're going to get some points here and there generated. But overall, it also kind of, if we look at these, it probably hugs the true boundary quite a bit. Over here, we have k equals 100. So we take a point and we say, what are the 100 nearest neighbors? The 100 nearest neighbors, some are going to be blue, some are going to be orange. And so the boundary that ends up getting formed ends up forming this kind of this line here, which doesn't fit the true boundary and the dotted purple line very well, okay? So these are kind of two extremes. K equal to 100 is going to have low variance but high bias. K equal to 1 will have high variance, low bias. Okay, so similar ideas that also apply even in the classification setting. And this is just for k nearest neighbors, and we'll discuss classification ideas later on. Here's something in between, k equal to 10. And here's the boundary, and we can see this boundary ends up following the true boundary pretty closely. There's certainly a little bit of difference there, but overall we can imagine for different data sets the amount of variance is probably not going to be as drastic as k equal to 1. Okay. I only have a few minutes left, but let's introduce the Tidy Models package, okay? And so in your first homework assignment, I think I just kind of linked things to Tidy Models. And actually, okay, so let me pause for a moment. If it's been a while since you've worked with the Tidyverse, you can learn the Tidyverse on DataCamp, okay? And so I got everybody's subscriptions to DataCamp. Yeah, question? Did you give us the second view quiz answer? Oh, I haven't given you anything. No, okay. Let's give you answers. Okay, second view quiz answer is the letter A as in apple, and third view quiz answer is E as in elephant. Okay, thank you for that reminder. Okay, so if I get, just remind me, okay? Because I want to make sure you guys get your points. So second view quiz answer is A as in apple, and third view quiz answer is E as in elephant. I think I just sent out invitations to DataCamp, and this is going to be a resource. I think DataCamp's a great resource. It's normally like $30 a month, okay? It's not cheap. It's a premium product. But I think it's very good as far as training, and they have a nice education program that, basically if you're enrolled in college and the instructor says you need this subscription. So anyway, you've been assigned, or I haven't assigned anything, but you can start working through some of this, okay? Right now, none of these things are mandatory. But if you feel like you need to brush up on some of these things, I recommend these would be the 3 courses that I recommend as far as refamiliarizing yourself with the tidyverse. They do take a while, so don't feel like you have to do everything in one sitting or anything like that. And if you are interested in more stuff, Data Camp, you can learn Python, and you can learn some of these other packages and things like that. It's a great resource. Okay, but anyway, let's get back to tidy models. And okay, and tidy models, what it is it's a bunch of packages. Okay, it's a bunch of packages that work together to allow you to do machine learning and model fitting in what we call the tidy manner. All right, and so again, assuming you've all taken 101A, you've already fit linear models and things like that. Okay, now when you fit LM, there's a bunch of stuff you can do. You can do summary on the model that you fit. You can do what are the coefficients and things like that. Okay, but sometimes, so if you do summary on the model that you fit, what do you get? You get this table of basically coefficients along with kind of p-values associated with them. And you look that up and you go, oh, okay, well, let's keep these coefficients and stuff like that. What tidy models will do is it allows you to kind of take that table and then use those values in future operations, okay? Because it creates basically a data frame out of the model outputs, okay? And it allows you to kind of create a workflow where you can say, hey, you know what? Let's not just take these estimates, but let's graph them and create error bars and things like that, okay? So the packages that work together in the tidy models, you've got RSample. RSample is used to kind of create splits between training data and test data. There's a package called Parsnip, and this allows us to work with different packages in R, different statistical learning packages in R. So there's always a debate between what's better, Python and R, and I have no skin in the game because I teach both Python courses and R courses, and I think both are great. Okay, they're different, but both are great. And this class uses R mostly because, well, Stats 21 is not a prereq for the class, and so if I started doing everything in Python, I think that would be a little bit confusing and troubling for some students. And again, I had high ambitions for the course, but I drew the line in saying I'm not going to also teach all of Python within our 6-week period. So we're going to use R, okay? Because Stats 20 is a prereq, but not 21. So, but anyway, one of the big differences between Python and R is for Python, there's basically one machine learning package. It's sklearn, okay? And everything runs through that. And if you're not familiar with Python and sklearn, don't worry. But basically, you want to fit a model, a machine learning model in Python, you're going to be using sklearn. There might be some other periphery packages, but pretty much everybody just goes through one. R, on the other hand, it's like the Wild West as far as packages go, right? You can write a package right now in your dorm room and then publish it, and it'll submit it to CRAN, and as long as it meets certain guidelines, it's going to pop up. And so there's a whole bunch of things. You've got a package for neural networks this and neural networks that, and you got a package that uses TensorFlow and a package that does support vector machines and things like that. And the interfaces for all of those things are a little bit different, so it can be a little bit frustrating. Parsnip says, hey, you know what? Parsnip's kind of like your translator, your C3PO that says, I can interact with all of these different packages and allow you to just kind of use one form, and I'm going to translate it into the different, what needs to happen for these different packages. So it's really great in that regard. Okay, you got workflows and Tune that will help you figure out your parameters, and Broom, which converts the output of R objects into data frames and stuff. So let me just kind of show you. Okay, so what I want you to do is I want you to work through Chapter 2 and Chapter 3 of Tidy Modeling with R, okay? And you're going to kind of read through it and stuff, and some of this you might not be familiar with, but so when you read, this is important, when you read this textbook, okay, especially with the tidy modeling with R textbook, you're going to see code chunks. You're going to see code chunks here, okay? Take the time to read each line in the code chunk. It's very tempting to just read the paragraph, see the code chunk, glaze over it, and skip to the next paragraph, okay? But please take the time to understand what is happening here. And it might be some command that you've never seen before, right? R sample bootstraps, you've probably never seen that command before. And, right now we're not introducing it, but at least take the time to say, okay, look up the documentation for any kind of function that you've never seen before, okay? And this slows down the reading, okay? And you're gonna be like, oh gosh, I don't wanna do this, okay? But at least just say like, okay, what is the purpose of this function, okay? And what are the arguments that come in? And you don't have to like understand everything to some super deep level, but please do take the time to read each line of code and just say, hey, do I know what's happening? When I see arrange empty cars gear, what does that do? Okay, and that's going to take the data frame empty cars and it's going to arrange them, basically sort the rows based on this variable gear, okay? And here it says slice, so we're going to take the first 10 rows, okay? Or that, okay? And here it says pipe it, so we're going to take empty cars and arrange them by gear and then slice the first 10 rows and stuff like that. So take the time to kind of read each of these things, okay? And here in this first chapter, it kind of gives you like bad code versus good code examples, okay? And see if you can understand why this one's bad and why this one's good and things like that. And there might be some functions you've never seen before, like map. What is map? Okay, and exactly what's happening. And map is kind of like an apply. It takes a function, in this case square root, and it applies it to basically a vector of values. Okay, it takes a function and applies it to vector of values. And here, why would we bother doing that with the square root function? Sure, we wouldn't do it with the square root function, but you can kind of create your own functions later on and do it. And so in your homework, basically I just say like, hey, read through this thing and just recreate a couple lines of these code. Same thing with chapter 3. Chapter 3 kind of works through creating a linear model, okay? Make sure you understand like how ggplot works, okay? And again, if you've never used ggplot before, take the time to work through that data camp chapter to remember how do we use aesthetic mappings and things like that, okay? And then, as far as creating models in R, you have the formula object, the tilde, predict rate based on time and temperature, or temperature and time, stuff like that. And take the time to read through this. But again, as you read through, try to understand each line of code that you read. And so, let me show you a little bit of some of the things that the tidyverse or the tidy models package does. Okay, so here we fit a linear model. Here, let me see if I can make this bigger. Okay, so here, again, assuming everyone took 101A, we fit a linear model to predict. This is on this crickets data set. Okay, so the crickets data set is like, I don't know if you are familiar with the study, but they said like how many times does the cricket chirp, right? It's like it chirps for like at night, and basically when it's warmer they chirp more, and when it's colder they chirp less, okay? And certain species of crickets will chirp more than other species of crickets. So we're going to say, hey, what is the rate of cricket chirping as it relates to temperature and species, okay? And And this is one model that gets fit, okay? And then so the full model looks at temperature and species plus the interaction of temperature and species, okay? The interaction, so here's kind of your graph. Is there an interaction between temperature and species? What are we looking for when we're looking for interactions? We're looking for lines that aren't parallel, right? So here we see for, whatever species this is, exclamationis. Okay, so that's one species of cricket. Okay, this is the slope that it gets. Okay, here's the other species of cricket, Niveus. I don't know what that is. I don't know anything about crickets. I mean, I know what they look like. Okay, and what we see is we basically see two lines that, for practical purposes, look parallel. Okay, so we don't see an interaction between temperature and chirping rate, temperature and species for the things. It's not like for one species, changes in temperature drastically affect the chirping rate differently from the other one. Okay, so we don't really see an interaction because these two lines are parallel. And so the first model that we fit, as you read through this thing, again, please make sure we first fit a model and we fit an interaction, okay, an interaction effect, okay, and then later on we fit a model that doesn't have the interaction, okay, and then how do we compare these things? Did you guys do this in 101A? You do ANOVA to compare, a complicated model with a less complicated model, or I'm sorry, the first argument is the less complicated one, and then the more complicated one, and then you see, okay, what's the p-value associated with the, using that additional degree of freedom, right? So the less complicated model, you have 28 residual degrees of freedom, and then for the more complicated model, you use up an additional degree of freedom for that extra parameter you're estimating, and it says, well, is it worth it? Was it worth using that extra degree of freedom? And here we get a p-value of 0.25, and we go, it wasn't worth it. It wasn't worth it, okay? And so we say, let's just stick with the main effects model without worrying about the interaction. And this is kind of how we do it in base R, okay? And then when you call, okay, well, let's the summary on this thing, you get this table, right? You get this table of the estimates and the standard error and the t-value and the p-value. And then you can make predictions based on that. And what we can do is we can, there's a function called tidy, okay? All right, and so this one's a little bit different, but we're using it. Here we did a correlation test between each of the variables and miles per gallon in empty cars, okay? And we get different values for each of these things, and we can tidy it, and it takes the output of the Pearson correlation test. So I don't know if you run a correlation test, but you get, the output of the correlation test is something like this, the t-value and degrees of freedom p-value. It prints it out like this, which is easy to read, but difficult to work with later. And so when you call tidy on it, it turns it into a data frame. And it basically takes all of this information, this t-value, the degrees of freedom, the p-value, and it turns it into, so this the test statistic is -8.9. It turns it into a column in this data frame, okay? And the p-value, all of these things. And it allows us to basically work with this. Now that we have a data frame, we can then kind of put it into as data for a ggplot and things like that, okay? So please, today, take the time to read through chapters 2 and 3. I've posted your first homework assignment, which is basically read chapters 2 and 3, and I just have you work through a couple exercises through it. And we'll end here for today. Sorry for going a couple minutes over. But that's that. And I apologize for the delay on the syllabus. I'll get that up and running, and we'll see you guys on Friday. So have a great day.